Someone has already a hand raised.
This is the powerhouse where the foremost innovators and entrepreneurs of the country team up with the smartest talent pool of students and faculty from IITM. The Research Park plays a catalyst that fuels unrestrained networking for future growth and business success while solving globally relevant problems. Space plays a vital role for business communities in shaping company culture. In the landscape of a thriving economy, the Research Park is located in the heart of the Tech Corridor in Chennai, lending homegrown expertise for global solutions. IIT Madras Research Park, the future of cutting-edge research and development.
Is she audible?
Richu, you're muted.
Yeah.
Okay, sorry about that. Hello and good evening to everyone. On behalf of the Office of Global Engagement, I am excited to welcome you to the 19th webinar from the IRIS webinar series. My name is Richu George Philip, and I'm a part of the Office of Global Engagement. From the Big Networks Technology Cluster, the research initiative presenting today is Network Systems Learning, Control and Evolution, led by Dr. Neerav Bhatt. This research initiative is a multidisciplinary center that aims to address fundamental questions arising in understanding man-made and naturally occurring networks like power grid, disease, and brain networks. Dr. Neerav Bhatt is an assistant professor in the Department of Biotechnology, IIT Madras. He is a core faculty member with Robert Bosch Center for Data Science and Artificial Intelligence and Integrative Biology and Systems Medicine. His research interests are learning, control and design of biological networks and reaction networks and man-made networks. Joining us as the moderator today is Professor Bayu Jayawardena. Professor Jayawardena is a professor in Engineering and Technology, Institute of Groningen, Faculty of Science and Engineering, University of Groningen, Netherlands. This group is interested in the two closely related main research topics, mechatronics and nonlinear control systems theory and its applications in diverse as aerospace, automotive, chemical processes, biological systems, energy, healthcare, manufacturing, and information technology. Thank you for joining us today, Professor Bayu. We're very excited that you could be a part of all the webinars today. Also with us on the panel are Professor Ramakrishna Pasumarthy, Professor Sridhar Kumar Narasimhan, Professor Arun Tangirala, and Professor Shankar Narasimhan. A warm welcome to you. Before we start, a note to the participants. Please use the Q&A to enter your questions and upload questions that interest you so that the moderator can prioritize them later. Over to you, Professor Neerav.
Thank you. Let me share the... Slides are visible?
Yes, sir.
Yeah, thank you. Welcome to IRIS webinar for CENS, Center for Network Systems Learning, Control and Evolution at IIT Madras. I am Nirav Bhatt, faculty in charge of the center. And I would like to thank Professor Bayu for moderating this session. All of you must be wondering, what are the network systems? Let me tell you that network systems are around us, within us. Some of the examples of these systems are power grid, water distribution networks, Twitter, Instagram, and list goes on. Each instant of our lives, we use these networks. They play important part in our lives, and it makes our lives smooth and enriching every day. Simple. And if their failure happens, think of no power in summer. The kind of exasperation we feel is unimaginable. The other kind of networks that are widely used are social media networks. They have a huge impact on our lives. For example, an influencer on the social media networks have a wider reach than the newspaper plus TV today when it comes to advertising or spreading the message to the masses. So what makes this kind of network structure? The answer is the interconnected world of social media. There are other kinds of networks that are within us as a being, such as metabolic reaction networks, vascular flow networks, brain networks, that actually allows us to function every day without any harm. And if there's something happens to that, we have a problem. The question comes to our mind is that why are we interested in having a deeper understanding of these networks? We have some understanding, but we want to understand furthermore. Let me take an example of COVID spread and 2012 Indian blackout. The top figure here describes spread of COVID-19 pandemic using genome sequence. The next strain is a project that tracks appearance of genome sequence of the virus from the patient samples to generate its map, where the circle indicates size of outbreak over a given date range, here December to February 3, 2020, in a particular country or region, and the line indicates where the virus has traveled from, a particular kind of mutant virus has traveled from. And we can see that the COVID-19 virus has spreaded from Wuhan, which is a small city, which we have not known 1.5 years ago or 2 years ago, to Europe, America, Australia, India within 2 months. And next 2 months, it spread over all the continents. And within 6 months, and still it spreaded whole world, and we are still affected by this virus. And this gives some kind of idea about how a small change at some particular point in the world has actually caused such a big event. Similarly, there is another network, which is a power grid network. In 2012, there was a huge power blackout. You can see here that a fault propagated half of Indian power grids and affected 600 million people. And there was no power for 2 days. And we can conclude from these two events that a small change in a part of networks may cause widespread and devastating effect on mankind. And that is the reason we want to understand some of these networks. It is apparent from the last slide that the whole is more than the sum of its part. But this may be due to the behavior of the whole depends on the interaction between each part. And hence the understanding of these interactions are important for controlling these networks. And in the future, designing the next generation man-made networks with the desired properties such as robustness, adaptation, resilience, and so on. And with this motivation, let me introduce how we are planning to achieve the goal of understanding these networks. So to achieve the goal of understanding these network systems, we take a bottom-up approach where the learning theory, control theory, and dynamical system theory are the foundation of our research methodology. And the objective is to discover the design principles of networks arising in a different application domains, ranging from biological or brain networks to the large infrastructure network, using the research tools and the data available from the different sensors, and apply them to the application domains altogether. As I mentioned that there are different application domain. However, these networks have a more similarity than you and I can imagine. And that leads to a fundamental question at the network level, a network abstraction level. For this network, we can ask first question is, how do these parts in the network are placed, the structure of the network, and their temporal behavior to give emergence of the property. This leads to a first question, how we can learn the network structure and dynamic from the data. The second question is about how do this interaction with each other produces network level functionality such as emergence, robustness, and resilience. And this leads to the second question, which about network structure, dynamics, functionality relationships, how we can actually identify and learn from the learned structure and dynamic in the first question. Once we address these two questions, the simple question comes to the human being is how we can exploit this understanding. That leads to the third question, how can we control these networks to avoid the failure or disaster, or how can we design a next generation networks, man-made networks, or retrofit the current networks to have a desired behavior or properties. Inspired from this fundamental question, our vision is to build a leading research and educational group in areas of network systems, learning, control, and design. To achieve this vision, our mission is a threefold. First, to address the fundamental research questions, which I have posed in the last slide, apply research findings to different network systems, different application domains, leverage from the fundamental understanding. And the third one is create a quality education material through courses and books, and provide a training program for capacity building in the nation. We have a unique advantage being at IIT Madras. We have a highly interdisciplinary faculty team. We have a talented human resources at a undergrad, graduate level. And we have other centers to collaborate at IIT level. And most importantly, if we have something to translate to the industry, we have an IIT Madras Research Park, which helps us to translate our research finding to the industry. With this, let me briefly introduce 4 research projects which are currently going on and their objectives. One of the networks that we are interested in studying is the biological networks, which is the biological networks in the cell, human cell, for the normal conditions, for the particular tissue or particular kind of organ, and disease conditions such as cancer or diabetes kind of condition, using the network and system theoretical approaches. One of the advantage here is the advent of data generation techniques and the open databases or sources in biology, which is typically not the case in many other fields. In biology, we are open and we have a lot of omics data and literature data available for many systems. In addition to that, people have started putting up the draft of the models or model they have created. Now, one of the main challenge is to integrate this multi-sensor data in seamless manner and construct integrated dynamic models. The first question we have is, do we have enough data to build a reliable model or integrated model? If we have enough data, then another question is, how can we build a model with a good predictability and in a temporal sense, which can predict a temporal behavior of the model, which is difficult to do for the large scale biological networks. Most importantly, how we can actually exploit these integrated dynamic models to develop a novel drug targets or therapeutic strategy using the control and design theory. So in this project, we are interested in answering these questions in collaboration with the faculty from IIT Madras and other faculty from IIT Guwahati, University of Groningen, University of Toronto. And the long-term goal is to build a personalized model and use it for a personalized treatment. The next project is related with the brain networks. Human cognizance is associated with a complex sequence of interaction between multiple parts in the brain, and we make different functionality take place. This interaction can be captured using the functional MRI data which are obtained through a set of experiments. In this project, we propose to use this novel data and the data-driven techniques based on the information transfer concept to evaluate the causal structure in the brain networks dynamics using the functional MRS data. Moreover, we want to use network control theory to compute the controllability of a property of individual brain region or entire network in the brain for particular task. Furthermore, we want to use the feature of large brain networks dynamics to actually learn or develop algorithms for discovering the neurobiological marker in order to distinguish patient with autism with healthy individuals. In the long term, the goal is to develop and apply a data-driven computational framework for identification of robust and the predictive brain circuit based on the markers of the mental health disorders. With this, here the collaborators are IIT Kharagpur, Stanford University, and Clemson University. Let's move to the more from the naturally occurring networks to man-made networks like process networks, which typically happens in many processes. It can be engineering processes as well as biological processes, where several variables such as flow, pressure, temperature dynamically influence each other and typically involve feedback and recycle. Discovering the underlying network structure of a large and multi-scale complex process from this kind of multivariate data present many exciting challenges. One of the exciting problems that is crucial related to reconstructing causal network structure from the data is information content in the data itself or measurement. For example, do we have informative multivariate data so that we can clearly reconstruct causal relationship between different variables from Z1 to Zn? If we do not have that enough information in our measurements, the next question is, what should be an appropriate excitation which we can give, which is input, and or experimental design condition to efficiently reconstruct a causal structure? A large question or larger question of the interest will be how it scales with the network size, with 10 nodes, 100 nodes, million nodes. Second class of problems are signal processing on the graph, which is based on novel graphical paradigm of signal representation. Systems are then viewed as a processors on the graph. We intend to apply the emerging formalisms of signal processing on the graph to develop methodology for monitoring this performances, these processes, and hopefully use this monitoring to yield measurements on irregularly spatiotemporal grid with application in distributed networks and weather modeling. The another kind of man-made networks which we are interested in is the infrastructure network in general, and develop methods for learning and understanding this network, man-made networks, such as transportation network, power grid network, water distribution network, and networks of networks such as climate infrastructure and social networks. Let me take a simple example to explain why we need to understand that, which is let's take a transportation networks. You must have heard previous speaker. Typically, we use Google Maps in big cities to find out traffic levels on the roads at a particular time and decide to take a route with the lean traffic. Imagine everyone makes the same decision of taking the same route with lean traffic. Then there will be a congestion on that route. Now the question here is, can we use this daily traffic data for learning a model of congestion in transport networks and use this model for understanding congestion in a particular city or a particular condition, like in the morning, evening kind of scenarios? And can we use our understanding of congestion to control traffic or provide suggestion to authority to improve the traffic condition? The main objective here is not to actually look at the particular network, but look at the network infrastructure network altogether, and come up with the method to model and control these infrastructure networks in general. With this, these 4 projects, we have been working on different aspects at the center and investigating different properties and look at the similarity between them. And that can only possible with the interdisciplinary faculty member team at the IIT Madras. We have at SENSE, where we have faculty from electrical, biotechnology, and chemical engineering department with a diverse background. And in the future, we will expand our team to the new members with more from the other departments with the different diverticals of skills. To advise our center, we have actually constituted a technical advisory board, who are Professor Vidyasagar from IIT Hyderabad, Professor Aryan Vandershaft from University of Groningen, and Professor Franco Bulo from University of Santa Barbara, California, Santa Barbara. And we hope that their advice and guidance helps us to achieve our vision sometime. Many of you have a question: how can we engage with the center? That's one of the important questions. We have a different way you can engage. If you are within the IIT, you can carry out your DDP or MTech project with us. Currently, there are 9 to 10 students are working with us on some of these projects. If you are outside IIT, within India, you can actually do summer internship, do project associateship, apply for a postdoctoral fellowship if you are have a PhD degree. And if you are aspire to get a doctoral degree, you can apply for the PhD program in the respective department, as well as interdisciplinary PhD program. If you are foreign national, you can join us through the Young International Faculty Program and come and work with us. With this, I would like to end my talk. I would like to thank all of you, audience, our students, faculty, and national and international collaborator and funding agency, but for supporting us with our endeavors. And with this, let me give the floor to Professor Bayo. Thank you.
Thank you, Professor Anirudh Bhatt, for a very clear presentations about your center. Actually, I'm very excited to see the center, which covers the complex interplay among many autonomous agents and systems. And as you have discussed during your presentations, it impacted our lives and its understanding as a crucial role in taming them and in possibly controlling them towards the desired outcome through the control theory. So when we are looking into your presentations, there are, of course, a number of questions that has been raised by the audience. All of them have been answered by some of the panelist members. But then I would like to probably open the first questions before I move to the questions from the audience. That is, in fact, in the broader domain that you have presented in your talk. So in your talk, you've presented that the network has played a role in a water network, biology, brain process, power network, and all of those things. And you have a number of faculty members coming from various disciplines. How would you foresee the collaborations among the different people? Are they still going to work on their respective network, or you expect that there will be some cross discussions or dialogue among them?
Okay. So
just an opening of a question before I move on to the next one.
Okay. Yeah. Thank you, Professor Bayu. So what we are envisaging right now is two kind of direction. One is the vertical as well as horizontal. So as I told in my presentation that we are interested in answering the fundamental questions at the end of the day. And but we all of us have our favorite application areas. So we are going to work towards those application areas as a research group, or subgroups in the center. However, the whole idea of having a center is to actually answer the larger questions. So I talked about infrastructure networks, where Ram and I work on the power grid networks, and Professor Sridhar and Professor Shankar Narasimhan works on water networks, and Ram and I also work on transport networks, and Professor Tangrela works on transport as well as infrastructure networks. So of course, we work on our field, but we'll engage ourselves to answer the fundamental question and come up with the more generic theories and more generic observation on network level applications and network level fundamental questions. Of course, our objective is not to disturb people from their favorite theory, but use that leverage from one field to answer the questions in other field. For example, in biological networks, what we discussed is bringing some of the control theory ideas and system theory idea to the network control theory.
Yeah, okay, clear. And as you have mentioned briefly that you are looking as well on the application side. Do you foresee any future collaborations with private partner, or whether there will be a public-private partnerships that will come out from the center in the coming?
So currently, we are looking at mostly government, means what we call institute funded or government funded project. However, you might have noticed that Professor Shankar Narasimhan and other faculty are actually involved in some of the startups, and they work, they do translation research. So we might contact, we tried to contact some of the industry and try to see if we can build a consortium over a time to have a private, public-private partnership and create a center which solve not only the fundamental problem, but also the problem in the industries.
Okay, so maybe I would like to bring some of the questions from the audience, but then I will try to phrase it from my own, with my own words. So there are questions on how can they interact with the center. Let's say students, you've mentioned before that they could participate by a number of activities, but can you be a bit more specific on how to do that? So there is a question from the students on how they can engage closely with the center.
Okay, so you can contact us on the sense@iitm@gmail.com. And what if I don't know the student's background? If he's is currently studying, he or she can apply for IIT Madras summer program in the third year. We have an institute summer program, or send an email to any of the faculty. If you are already graduated and looking for a project associate position, you can send an email to us with your CV. As well as time to time, we'll put a ad for different positions available on the centers. And if, of course, you are a postdoctoral fellow, again, you can send an email to us. So there are, just send an email to us, either me or any of the panelists on our team member, and we'll get back to you with the appropriate position at the time.
So there are multiple ways, but then for sure they have to contact all of you through this email address.
Or one of us, depending on their area of application or their area of interest.
And one thing that is attract me most as well from the center is that it has quite a broad international network. You mentioned about the connection with the United States, connection with Europe. How can the student engage with those institutions? Because you would like to build the capacity within India.
Yeah, so one of the idea we have is to actually, over a time, come up with a joint degree program with some of these institutes, if possible. We can start with exchange. Currently, our Dean G's office is actively engaged in sending, getting a student from abroad, as well as our students to go and travel abroad for research group. And the longer run, we can actually come up with a joint degree program, and where students can actually enroll and have an experience from, have a degree, enroll either in the partner institute or here and get a degree from the Bose Institute, as well as spend time in the Bose Institute. That's a longer goal of the center. Maybe down the line, 2-3 years, we want to have those kind of joint degree doctoral program as well as master programs.
That's a really interesting proposition that you put there. So I'm looking forward towards that really close collaborations between all of us with the IIT. And there is also questions in engaging with the center. It is coming from the faculty member. How could the other faculty member be engaged with the center?
Sridhar, you want to answer that question?
Maybe other people would.
Maybe other people can answer.
Yes. Professor Ramkrishna or Professor Sridhar, or Professor Arun.
Yeah, I can answer that. So as a faculty member, you can, I think you can apply for, you can first inquire with us what exactly interests you. I think that's very important, because as Nirav just presented, the center's research interests are fairly broad and diverse. We would like to know from you what particular research project interests you, and once that's understood, then there are different ways to engage. Either that you start a collaboration without any external funding, if there is mutual interest and the skills are also complementary, or write a joint proposal for funding, right? If there is a project that's existing and one of the faculty members, colleagues are already working on it, and if your skills are complementary to the existing skills, then we will invite you to be a part of the project and so on. So I think the first step is to write to one of us and tell us what aspect of the research projects interest, and then we can take it from there. But yes, there are many ways to engage.
Thank you, Professor Sridhar. Clear. There is a question, a technical one. Maybe one of the panelist members could answer as well. This is related to the influence of the network size to the way we understand about the underlying physical processes. Is there any general statement that can be made? So the precise question is as follows: how the size of a network will affect the inferences towards the physical processes, mostly climate networks? Anyone would like to address that questions?
Arun, would you like to take? You work on the climate networks.
Sure. Yeah, so Danish, welcome to the event. So the size of the network depends essentially on the size of the problem that you're looking at. And if you are referring to climate networks, you know very well that climate networks are built at different scales, spatial scales. And if you're looking at a finer spatial grid, then of course the size will grow. So to answer your question specifically, if you are trying to reconstruct a large size network from data, then certainly you will need more data. So, but if your data is fixed, then as the size grows, our ability to estimate or reconstruct such a network will obviously go down. It's like, I mean, you can equate the size with the number of parameters in a model. I think if you understand a bit of data science, the size of a network is equivalent to model complexity. The more complex the model is, the more data you will require. So obviously, the inference now, a reliable inference, will call for more data. But then the advantage is that you will be able to do a fine grid prediction and so on. So that's it. I think for climate networks, as you go finer and finer, you'll require more data and larger size.
Okay. I hope that answers the questions from Danish Mansoor. There is a question that has been answered actually by Professor Arun, but I would like to bring this up again to the discussions here. And that is about the topic of network science, which is seen to be reinventing the wheel from the other discipline, particularly from statistics. Just now, it has been brought up as well that the role of data and model also being combined with the network. I think that is one of the new element that is currently becoming more popular on how we look into the interplay between the underlying model for every autonomous systems and the connections among the agents through the network. But maybe other people would like to comment on that as well, whether you have another opinion about the reinventing the wheel from the network science, for the network science, I mean. It's a question by Hari Prasad Faradayan.
I've already put in my answer, so if anybody else wants to answer, that would be good.
Sorry, okay, I can say something.
Go ahead.
So I think, it may seem like reinventing of the wheels, but you see the kind of problems that existed, say, 20 years ago, and the kind of problems that exist now, even say technologically, if you look at Internet of Things, or you look at, or what they call also of Internet of Everything, where everything or everybody is connected to each other. So I think the scale has increased, the computing power has increased, the computational capabilities have increased. So it's, even though maybe the tools you can be traced back to statistical physics, you see how the tools mature to handle the problems that are that the current challenges that we face in terms of, say, anywhere from engineering networks to not just social networks, but also looking at what is happening with the pandemic, of say, for example, how to vaccinate. Should we really vaccinate all the 100% people, or should we do targeted vaccination, and so on? So I think the problems that we keep facing are kind of changing quite a bit, and that kind of involves also fine-tuning existing tools, or even maybe looking at it from a different perspective altogether. So that's my two-line answer. Maybe Professor Bayu can also say something on this experience.
No, I think I agree with the answer from Professor Shankar as well. So I think from my point of view is that the fact that we are incorporating some can be complicated dynamical model to every node, that at an additional level of difficulty in analyzing the network science. So that's why we have this dynamical network that we have to study as well. I think that's from my own side.
Hey, this is Sridhar here. Maybe I can also add a pointer. So Ramakrishna mentioned about new problems which were not there several years ago. Another counterpoint could be there are problems which existed then, but the kind of data, both at the scale and temporal and spatial resolution that you're getting today, did not exist many years ago. For instance, water networks have been around for nearly 100 years, but today now it is possible in principle and in practice to collect flow data, at very, very fine temporal scales, and also even spatial, at reasonably resolved spatial scales. So this kind of information was probably very difficult to obtain in real time or in quasi-real time maybe some years ago. So what I'm trying to say is that availability of data in quasi-real time also allows you to do things which were not possible years ago.
Okay, I agree with you as well, Professor Sridhar. And I would like to propose that we try to address some other interesting questions from one of the audience, and that is about the future technology. What would be your visions of the future technology that can come up from the center related to the network technology? Anyone would like to shout their idea? It's a question from Kalai Manivel. Maybe Professor Nirav?
Yeah, okay.
Any visionary answer to that?
Yeah, okay. So the technology is a little different from the science, so I'm a little confused what I mean by technology. So what we are expecting, at least I can say, we are expecting that we can come up with some algorithms which we can actually implement in monitoring and control of power grids or water distribution networks, particularly currently water distribution networks. Sridhar and Shankar sir works quite often, and they have actually shown good amount of translation, if I can say, at least at a small level, and hopefully over a time this technology can be scaled to a larger scale. Similarly, some of the ideas we have been working on building a network, integrated dynamical network, biological networks. We are hoping that we'll come up with a wholesale model for certain diseases, and that can be used for come up with the network targets, or a technology which allows clinicians to understand how actually integrate the temporal data from the patient measurement at different time of treatment to provide better and better treatments. So those kind of 2-3 technology, I can see that it is possible to come out over the next 5 to 10 years. and hopefully we can translate it and make it reality is our goal.
I think if I'm allowed to think freely, maybe I can try to chip in into the idea.
Yeah.
When you talk about the water networks, when you talk about biology, something that come up directly to me is that potentially we could also have a technology which allows us to have a predictions of a biomass buildup in the water networks simply by having a measurement of data, biological data at some point in the water network, and then we can pinpoint some of the buildup of biological processes within the transportation network. Maybe that is one thing that I can imagine as well.
Okay.
Anyone would like to chip in into that one?
I want to also say that some of the ideas that we are going to learn from this is how to design these networks. There might be some structural properties that impart, for example, people are afraid that some of these networks can be attacked, even water networks, just like computer networks can be hacked. Is it possible to build a network that actually, even if it's attacked, only affects a very small section of the people? That design might be quite different from the way the tree type single source, what I call centralized networks that we have built in currently. Future things, I mean, in order to combat these kind of threats, people may actually have much more distributed kind of networks which are resilient and less prone to attacks, or even if they attack, less prone to affect a large number of people. Those kind of principles may actually emerge, which can be used not just here, but also in computer network design and so on. And perhaps in the biological field, can we actually kind of reconfigure some aspects that will actually make it disease resistant? I mean, that's the kind of thing that, or either through intervention of a drug or some other means. I mean, these are kind of things that we are hoping that our what I call research will reveal.
I agree. So you're talking about the aspect on the design of the network itself. Yeah, I think
I can maybe just buy you. If
go ahead. The last answer. Go ahead.
Yeah. So Shankar talked about design with and make it resilient. We have also seen how network structure, in fact, with Varghese, who's also was attending as a panelist, as an attendee, how networks, especially water networks, how the structure can affect operability or controllability. So are there other network structures which are easier to control?
Yeah.
Or which allow you to make them more operable. And maybe also controllable in the traditional sense that we know of state-space controllability, but definitely in terms of operability, are there other network structures which make these easier to operate?
I agree.
We are interested to see whether these findings have relevance in other areas, other networks such as transportation networks, communication networks, and so on.
I agree. So it is like identifying some agents or nodes that can be controlled easily with a less effort than the others.
Yeah. That's part of the question. The other thing is the design itself. Are there certain topological properties of these networks in terms of how deep they are, or what are the degrees of these nodes? Are there certain networks which are easier to operate and certain networks which are more difficult to operate?
Yeah. Okay. Thank you.
Yeah.
And I think given the time, I would like
last comment.
Yes.
So it has been asked by a faculty. So it's about a workshop and any summer schools. So we are planning to have a winter school. If things goes well, we want to do one-to-one or in-person winter school, or we definitely summer school. So maybe we will actually announce soon about some of the winter schools, as well as some of the tutorial sessions in control conferences we are going to organize. And of course, if it will tell to the audience that these are the places, and you can always subscribe to that and learn more about network systems and some of the idea related to research. Yeah, thank you, Bayu.
Thank you, Professor Niroklat, for the final remark about the possible winter course and winter school and summer school. And I would like to thank all of the attendees as well for attending this seminar series. And I would like to give the floor back to Ritu.
Thank you, Professor Bayu. Thank you to Dr. Neerav, thank you Professor Bayu and everyone else on the panel. It was a really wonderful webinar where you've explained things in detail and taken a lot of questions from the panel. Professor Arun had taken his time out and written really great responses to it also. So thanks to everybody on the panel. Thank you to all of the participants. We do have another webinar coming up on August 5th. Hope to see you all there as well. Good day to everyone. Thank you. Thanks again, Professor Bayo. Thank you. Thanks to the entire.
Thank you, everyone.
Professor Bayo and everyone. Yeah.
Thank you. Thank you, Dr.
Thank you.
Bye.
Bye-bye.